So, as yes, this is the presentation on the syntax dialect. Here's the outline of the talk. First, we'll give why am I interested in this. Then we'll expose the syntax dialect and what we can do with it. So the motivation for it is that in my dissertation, what I wanted to explore is more modular compilers and languages. And one of the things that this led me to was to explore dynamic parsing combinators. So for example, on the list and on the right, what we have is like some code, but the main compiler doesn't need to know what OMP or GPU or MLIR is in the code. So I needed a way to say, hey, once you encounter the keyword, let's invoke the parsing combinator. And so basically that is the main motivation of why I needed this, because there were no existing tools that provided me with the flexibility for this. So I ended up building one. So the syntax dialect, it's just a high-level description of formal grammars. Like if you see on the figure on the list and on the right, you'll have your traditional things like terminal, ands, or zero or more. So it's pretty. It's able to represent all your traditional expressions, but there's also some high-level syntactic features, like for example, functions over the syntax. So you can use like you can create something like a macro to interleave. Like for example, if you ever used LLVM core, you have like interleave comma or interleave. So this ends up fulfilling the same function where you can just say, let's have like this generic function and let's apply some use it to create new expressions. So, and the dialect itself also has dedicated operations for lexical and syntactical analysis, which we'll see later. And yeah, on the list on the right, we also have like how the IR changes after MLIR inline, which just simply inlines the macro function, and this is pretty helpful for when you are trying to have like something like interleave, which is pretty common. So with this means that you can just have one interleave and start reusing it. Now, one of the things in terms of the design is that most operations are either pure or constant-like. In terms of MLIR, this means that they have no side effects or they behave like a constant, which means that we can use CSE or common sub expression elimination to optimize the redundancy. So for example, on the list and on the right, what we have is at the bottom, at the top, a listing for a rule that has some redundancy because you have AB or ABC, which means that you are computing 2 times and AB. On the bottom, that redundancy is eliminated by CSE. So we can use traditional optimizations to even start optimizing like a formal grammar. Now, in terms of lexical analysis with syntax, we create, because my end goal was being able to generate all of this and build a compiler, so I created like a table gen backend to create these syntax analyzers, which in the end ends up meaning that this project is fully dependent only on LLVM and MLIR. And it starts with a pretty high level description in table gen, just saying, hey, this is just going to be one of the rules, like for an identifier, and that will produce like the full MLR code. Then this MLR code gets analyzed and optimized and then translated into C++. In terms of the implementation for the lexers, they are just based in their traditional DFA algorithm. In terms of lexical transformations, we begin with inlining and canonicalizing and applying CSC because we also have like some canonicalizations to just remove. For example, if you have 0 or more, and inside the 0 or more you have another 0 or more, then you can say that is just 1 0 or more. Then we start transforming the IR into a DFA. In this case, the DFA is not minimal, but it already has like all the elements to create like the lexer. So you have your states and your transitions. Then we perform traditional DFA minimization, which then we can finally use it to generate C++. And in this case, this is pretty straightforward, but it has the benefits of that you can also modify these lowerings, so maybe you could further customize this to one's needs, which was the main point of creating all of this. So now with syntax analysis, with syntax, it's the same gist. Basically, we also created a table gem backend for this. In this case, the list on the right shows one of the features that we needed or that we wanted in our compiler, which was like dynamic parsing combinators. And that is shown on line 14, where you have the @dim3 is a macro. So it means that expression inside a hashtag dim expression is going to go through the parser macro, and hashtag dim expression, it is just saying, hey, I need you to invoke the dynamic parsing combinator, which allows to basically have extensible syntax on demand. And in general, there's no limit to what you can introduce for new ideas in terms of the parsing, or in terms of the parsing. So this means that all of this is quite flexible to start incorporating new ideas. And as it also can be seen on the figure, it has support for saying, hey, I need this code block being executed after this. So it is pretty nice to start working on things that are not traditionally supported by other syntax analyzers. Now, in my particular case, I was interested in generating parsing expression grammars instead of traditional things like parsers or LR parsers. So, and as I said before, this has native support for dynamic parsing combinators. So it's pretty straightforward how you can use it to create like new parsing of some code. Now, in terms of the syntax transformations, we started with the table gen code, and so it's pretty standard. In this case, is A or B, or the AOC or COD, and that is just the parser, and it just has one rule. And then we start performing inlining, canonicalize, and apply CSC to, again, start removing redundancies, get rid of all the macros, and have like one coherent syntax. Now, after this, what we do is we analyze the grammars, and we start saying, we start saying, hey, maybe we can optimize this. Because if you know about parsing expression grammars, they are basically recursive descent parsers. And if you use packrat, they might be a linear time, but then that means that you have like a bigger memory footprint. What we found is that we can actually further optimize that, because in many cases you can make decisions of local decisions of when you don't need to backtrack to a previous state. So for example, in this case, this is materialized on the IR by having switch and any expressions. So if you remember, the initial parsing rule was A or B and A, or AC, and the other one was like C and D. So in this case, the analysis determined, hey, you can actually switch and fully determine which branch are you gonna take based on the first the first token. And in this case, the switch will go either to the any on line 15, which is I need to backtrack, or it might be going to this line 14, which is like an AND operation. So in this case, this means that we can make local decisions and remove some backtracking that might not be needed, which ends up improving performance. Now, in terms of future work, which is the part that interests me the most in this project, is being able to JIT compile this dialect. So this means that we have like a grammar, and in that grammar, we can take it directly to LLVM and then use the execution engine and being able to execute it right away, which in this case means that we can have LLVM optimized regex recognizers on the fly, which might perform better if you have like a system where you require to perform many regex queries many times. This might end up saving time. And the other thing that I'm particularly interested is in the possibility of self-extensible programming languages, where if you can have like a JIT this out into a syntax, then you just need to put that model at the top for creating new syntax, and then you can reuse that function later on to parse new syntax, and the syntax was declared in the same language. Now, the biggest barrier for JIT compilation in this case is that all the runtime that was created for doing this is heavily reliant on C++, and like, for example, standard optional. So you need to transform that into more friendly C code to be actually able to JIT compile. So the summary is, well, with syntax we can create and analyze lexers, also syntaxes, and we find that this means that we can apply traditional compiler techniques to even optimize things like formal grammars, which in the end ends up proving how MLIR is an useful infrastructure beyond just traditional compilation. So here's the acknowledgements and some questions.